Good afternoon, everybody. So my name is Tim Bender. I'm a member of the Department of Chemical Engineering and Applied Chemistry here at the University of Toronto. And today I'm going to give you a 7-minute pitch about what we do in my laboratory, and specifically titled Parading Around the P block of the periodic table in this group of organic materials called Phthalocyanines. Just to give you an overview of my laboratory, the goal of our laboratory is the design of new organic semiconductor materials for photovoltaic applications and proof of their functionality. Now, I'm going to show you one functionality called pentafluorophenoxy group today. I've added that to my title as a point of discussion. This is the outline. There's the P block. These are phthalocyanines. But here is the generic phthalocyanine shown here. And if anybody here is actually wearing blue jeans, so I notice that Ian is, for example, you may actually have phthalocyanines in your pants. And phthalocyanines are what we call colored rock. They are pigments used in the coloring industry, highly insoluble materials, but highly colored in the blue and green space. Now, early on in my appointment here at the University of Toronto, we got interested in a very unique phthalocyanine, which is the so-called boron subphthalocyanine, which, if you draw it in 2 dimensions, it looks like a standard planar aromatic organic semiconductor molecule, but if you look at it in 3 dimensions, it's actually got this very unique bowl shape. And what is unique about this is that we can use boron chemistry at the axial position, shown here, to convert boron subphthalocyanine into dyes, engineered crystals, which look like fool's gold, and sublimates for incorporation into OPDs. And so let me just show you why we were interested in this subphthalocyanine specifically, is because its absorption is very close to the maximum flux of photons we get from the sun. This is solution state absorption. This broadens significantly in the solid state, and in the solid state we can grab up to about 38% of the photons we receive from the sun with a single subphthalocyanine molecule. Now, early on, what we did was we did, again, that boron chemistry and converted chloride to pentafluorophenoxy, and that allows us to tune the homo-luminal energy levels. And you can see from this band diagram, for those in the organic field will know, that pentacene, or 5-cene, is a known electron donor. C60, or Buckminster Fullerene, is a known electron acceptor, and you can see that these subphthalocyanines fall in between. In other words, they should be duly functional. And what we showed with our collaborators in Neil Armstrong, University of Arizona, is that if we did actually take these materials and pair them with C60, they function very well. And if we paired them with pentacene, or oddly enough, put them together in an all-B sub PC cell, they also function as electron acceptors. And so we have this dual functionality built into one particular molecule that also strongly absorbs the sun. Now, hopefully that was about 3.5 minutes. In the other 3.5 minutes, I'll tell you about how we've been interested recently moving away from boron and into the other parts of the P block. Now, for those people that might know organic and inorganic chemistry, you know what this red zigzaggy line is this is the metalloid line. So things to the right-hand side are metalloid, like boron, and to the left are metals, like aluminum. And so we want to move around this space to see if we could do this pentafluorophenoxylation and other chemistry at the metal center to affect the photovoltaic properties of the resulting phthalocyanines. Now, you can see here, X's mean no, triangles mean so-so, and green is a yes, and I'll show you today the case of silicon. Now, the first thing we did was screen silicon, germanium, and aluminum phthalocyanine. These compounds are known in the pigment industry and known in chemistry. And we determined, again, their band structure, and again, that they could be duly applied either as acceptors, or as donors, with C60 receptors with pentacene. And so what we found when we paired each one of these with carbon-60 as an electron donor, they were all pretty much crappy, except for the known fluoroaluminum, which Frankie Soto of Florida had shown some time ago is a very good electron acceptor, or electron donor, pardon me. But when we paired them up with pentacene, what we found was that, in fact, aluminum was one of the best acceptors, but oddly enough, silicon also started to have very reasonable photovoltaic properties. Now, these type of JV curves cannot be compared against the ones like Professor Lapierre put up, because these are organics, and again, we're not device people, we're just trying to show functionality. But this was very encouraging to see that silicon was starting to have photovoltaic behavior, and for those who know what triplet harvesting of pentacene means, also that we could start to harvest the triplets from pentacene with these materials. Now, if we look at what happens when we take silicon, the chemistry of silicon phthalocyanine is actually fairly well known, and what we did again was put our pentafluorophenoxy fragment on there, and what we found was a humongous increase in the VOC, up from 0.2 to 0.8 volts. And because, admittedly, this presentation is being taped, I will tell you some unpublished results where this curve goes to here. Okay? You see that, right? I'm not going to say what the number is. Okay? But this number is starting to get down here, still not close to what was left here put up, but again, the silicon is showing extreme potential as an acceptor in what Professor Hill's going to talk about, fully free photovoltaics, and also as a triplet harvester. That's 7 minutes, I hope. Questions?
Questions? I have a question.
Certainly.
Can you tell us the efficiency you get from this new magic molecule? Or
I'll put up some fingers. How's that?
okay. Great.
Just because the manuscript's in preparation.
Okay.
Thank you.